Just like you can find the slope of a tangent line to a curve on a rectangular system, you can also find the tangent lines of polar graphs. Create a formula for dy over dx given a polar equation. Use x equals r cosine theta and y equals r sine theta. So I'm going to begin by deriving x with respect to theta. This will require the product rule. First function times the derivative of the second plus the second function times the derivative of the first. Remember, we're deriving with respect to theta, so deriving r with respect to theta will not be 1, it will be dr d theta. Let's derive y with respect to theta. Just like our rule for parametric, dy over dx is equal to dy d theta over dx d theta. Therefore, dy dx is equal to r cosine theta plus sine theta dr d theta over negative r sine theta plus cosine theta dr d theta. In order to use this formula, I'm going to need to know what is dr d theta. Well, guess what? I have a relationship between r and theta right here. So I'm going to distribute the two and then derive both sides with respect to theta. The other values I would need for this formula are r and theta, the point. They already said the point is 2, 0. Because if you plug in 0 for theta, you get a radius of 2. Now I'm going to evaluate dy dx at 2, 0. R is 2, theta is 0. Dr d theta at 2, 0 is negative 2 times 1, negative 2. So I plug that in for dr d theta. Because the equation of our tangent line is rectangular, meaning it deals with y and x, our point should be in rectangular form. 2, 0 is actually the same point in polar form or rectangular form. So our equation is y minus 0 equals negative 1 times x minus 2. For example 2, we're going to find the points at which the graph of 2 minus 2 cosine theta has horizontal tangents. 2 minus 2 cosine theta is a limacin. Let's go ahead and graph this limacin to have a visual before we evaluate the horizontal tangents. To do that, I'm going to graph this on a rectangular plane and then transfer those points onto the polar. Zero, 0 is also at the origin. 2 pi halves is a radius of 2 at the angle pi halves. 4 pi is a radius of 4 but at the angle pi. 2 3 pi halves is a radius of 2, angle of 3 pi halves. And back to 0 2 pi, a 0 radius, it doesn't matter what your angle is, you're going to have a point at the origin. Because we don't have an additional point over here, I know that this one is not going to have a loop, but because it did go back to the origin, that means I'm going to have a cardioid. To find the points on the graph where the limacin has horizontal tangents, we're looking for where dy dx is equal to 0. First, let's find dy dx and then make it equal to 0. I have a value for r, and that is 2 minus 2 cosine theta. Oh no, what's dr d theta? Dr d theta is going to be positive 2 sine theta. So we'll replace dr d theta with 2 sine theta. Since we have dy dx, we can now make it equal to 0, which would make our numerator equal to 0. And in this step, I'm going to distribute my numerator. Here I have an equation that I need to solve that has cosine, cosine squared, and sine squared. If I could turn everything into terms of cosine or cosine squared, then I could factor. Sine squared is equal to cosine squared minus 1. Continue simplifying. Now let's factor. Use the zero product property to solve each of these for theta. The theta that satisfies cosine theta equals negative 1/2. Cosine is negative in quadrants 2 and 3, so that would be 2 pi thirds and 4 pi thirds. Cosine of theta is 1 when theta is 0. And visually, we can see that that does make sense. The 2 pi thirds angle is about here, 4 pi thirds is about here, and 0 is about here, all where we have horizontal tangents. To find the equations of the lines tangent to r at the pole, let's begin by graphing r. This is a rose petal curve where n is odd, meaning we're going to have 3 petals. Our max radius is 4, and we'll have y-axis symmetry because we're working with sine. Okay, with this description, we really only have 2 options. This one or this one. To check which one it is, I'm going to plug in pi fourths. At pi fourths, the radius is 2 root 2. So when our radius is 2 root 2, so around here, pi fourths is our angle. That is matching up with the purple petal. Obviously, I drew those too long. Let's fix it. We're looking for the tangent lines at the poles. To find theta at the origin, make r equal to 0. Sine of what angle would give me the value of 0? That would be sine of 0 or sine of pi. In fact, I could rewrite 0 and pi thirds as an expression that covers all pi thirds angles that are relevant to this problem. That would be 0 plus any amount of pi thirds. So n pi thirds is how we write that in general form. Therefore, theta is equal to n pi thirds. So theta can be a multiple of pi thirds. I only have 3 tangent lines, so I'm going to start with the first 3 values of n, where n could equal 0, which makes theta equal 0. That looks like the slope of y sub 1. We have n equals 1, where theta would be pi thirds. That looks like the angle for y sub 2. When n equals 2, theta is 2 pi thirds. That looks like our last tangent at the pole. So we are done, because we only have 3 tangents at the pole. Now, instead of using point slope form, I'm going to use the idea that tangent of theta is equal to y over x. And if I solve for y by multiplying both sides by x, I literally have y equals mx plus b. So you have your slope-intercept form right there. So if you only have an angle and you know that it goes through the origin, then we don't need to consider any other points, and we can create the equation of each tangent line. I'm going to plug in 0, and that is 0. our second equation of the tangent line. We will plug in pi thirds, making the slope of y2 root 3. Visually, this does make sense. And here are the tangent lines at the pole.